Hello. Today's presentation is going to be looking at an overview of the AIAG and VDA Guideline with a specific focus on the PFMEA. I will be doing another one for the Dfmea, and some of the introductory slides will also cover that Dfmea as well. This presentation is referencing the AIAG 4th edition of 2008, the VDA 4.0 of 2012, and the AIAG and VDA 1st edition of 2019. Wherever references have been made verbatim, the exact written statements have been reproduced for clarity, and these are denoted by a red star. This is from the Fmea handbook, as well as any of those handbooks. You can purchase the current Fmea handbook from the AIAG website, and there you can read and make your references as well. So welcome and thank you for being here. My name is Desmond Mahadio. I'm a management consultant with over 20 years experience in the automotive industry, in manufacturing, in other sectors as well. I have worked in service, distribution, logistics, and warehousing, and also in different operations as well. I am a Lean Six Sigma Black Belt, a certified quality engineer from the American Society of Quality, and my background is I've got a Bachelor's of Science in Mechanical Engineering. I'm also a Quality Management System Auditor for both the IATF 16949 and the ISO 9001 2015. Some of the things that I've contributed to are the development of standards at the ISO level and the international level. I was fortunate to work on the recently completed Innovation Management Standard, or the IMS, and currently I'm working on the Strategic Intelligence Management Standard, which should be published sometime next year. The work for the standards development encompasses working with over 45 member countries at the international forum, which are held annually in very many different countries. So I've attended quite a few summits in Japan, Stockholm, in North America, etc. I have worked in operations management, management consulting. I've spoken at several conferences and seminars in Canada and in the USA on topics of organizational excellence, risk management, both at the ASQ Forum for their sections in Toronto, Hamilton, Kitchener, and also for the section in Detroit for the automotive section. I've spoken at the GYRS conference, and I was able to speak at the SAE conference that was going to be held in 2020. However, that was cancelled, and that would be done as a recorded event. I also worked in continuous improvement using Six Sigma and Lean to drive improvement. My forte is quality management, for which I've spent over the last 2 decades managing, implementing quality management systems for different types of industry. I've also done risk management with a focus on FMEAs specifically, and had training on the new AIAG and VDA publication, or guideline as they call it. I've done training, mentoring, consulting, teaching, and I instructed at the Senegal College in Canada for quality management system. I'm the current ASQ Toronto chair for 2021. Right now I'm the chair-elect for this year, and was a past ASQ Deputy Regional Director for Canada. Up in the right-hand corner, you'll see, just to give you an idea of my location, that's the section of Canada, and I am in Toronto, which is one of the major cities in Canada. So in this presentation, I want to explore by using the standard approach. I want to use the what, the why, how. I want to look at some methodology, both that is employed in North America and Europe, look at harmonization, look at some limitations of the methodology. I'm not going to go into in depth. I will probably do a special in-depth session on FMEAs that would show you exactly how to do the FMEA at a very detailed level. But this is merely an overview to get you to understand how FMEAs are done with a focus on PFMEA. So let's start off with what? What is an FMEA? An FMEA is basically stands for failure, mode, effect, analysis. It's commonly called loosely sometimes FEMA, which means is Fmea. FMEA is basically a very analytical risk management methodology that can be used in the automotive, it can be used in service, it can be used in any industry. And what it is it's a discipline technique. So you're trying to identify and eliminate in design and process any potential failure modes that you see. It is basically a preventive method. There are two types. There's a Dfmea, which is the design failure mode effect analysis, and a PFMEA, which is process failure mode effect analysis. So let's look at these terms so that we can understand clearly when we talk about modes effects analysis. What is a failure mode? The failure mode is the way in which something can fail. So basically, any components of assembly, product, process, how could it fail to perform its intended function? That is your failure mode. The failure effect. So if this failure occurs, what will happen? What will be the effect of it? There's going to be an impact. There are varying degrees of impact, and the impact is coined as severity, the severity of the impact. When we look at failure analysis, what we need to look at, what is the probability, what is the frequency that this thing can occur based on the system that we have in place, the detection system, the prevention mechanisms that we have. And in the analysis, we want to take actions to mitigate those identified failures. We have to put some sort of a ranking system, create an action prioritization of the risk, and then we would also need to look individually at the severity, occurrence, and detection to understand what action needs to be taken, when it needs to be taken, and ensure that it's closed out both in the design and in the process development. So we've covered the what. So now let's look at why. Why are we doing FMEAs? To understand why we're doing it, we need to take a step back. We need to understand, first of all, some history of FMEAs. I have here a timeline. So in the post-World War II era, in the 1950s, the US military and aerospace, they were targeting prevention in design, prevention in also assembly of those designs, assembly of the products, and they were doing what is known as Fmea, failure mode effect criticality analysis. This then evolved later into the 1960s in the space program, where we had operations research teams, which is commonly known as OR, from where we saw things like PERT, program evaluation review technique, some of the early stages of really extensive use of project planning and Gantt charts, and also as a risk management tool, the FTA or fault tree analysis was introduced, which uses Boolean algebra, and you've got your and your OR gates for those of you who are familiar with FTA. This progressed until the 1970s, by which time some popularity was gained because of its effective and efficient use in design as well as in process assembly. So we saw quality and reliability engineers really using this process because it focused on actions to eliminate or reduce any potential failures prior to actually producing the part. Then came the 90s. By the 1990s, the AIAG, which is the Automotive Action Group, Automotive International Action Group, that is based in North America. That is the body that governs the combined efforts of the three OEMs, the big three as we call it, which is Ford, Chrysler, GM. They, in 1993, published what was known as the first edition of the failure mode effect analysis to make it formalized for suppliers to use one standard method of doing FMEAs. In 1994, the SAE, which is Society of Automotive Engineers, since they had a lot of influence into the automotive industry, and standards published by SAE is used extensively by the automotive industry. They published and they endorsed that AIAG first edition, and it was exactly a write over of the AIAG first edition. And that standard was the SAE 17, the J1739. In 1995, meanwhile, over in Europe, they also established their version of a failure mode effect analysis. It was not just a form, but it was a completely different way of looking at things, and their approach differed from what was being done in North America. After I would say about 2 or 3 iterations, we came up with in 2008, which was considered the golden standard. 4th edition was published, and in 2009, the SAE J1739 adopted the 2008 and also published that. So for those OEMs that were using the J1739, it was now all standard. That golden standard continued and up to today is still being used. In 2012, the VDA did some revision over in Europe and they published the VDA 4. And around 2016, the AIAG set up a task force with the VDA so that they combined efforts and create what is now known as the 2019 version or Rev 1 of the AIAG and VDA. And that is what this presentation that I'm going to be looking at. What are some of the changes and how this is compared to the VDA. So again, having looked at some historical perspective, let's look at risk management. Risk management today is more critical than ever before. And to understand this, we need to just do a quick review and go back from Industry 1, as they call it today, to Industry 4. In 1784, as we all know, there was a lot of mechanization, there was a steam power, there was weaving loom, there was a printing press. At that time, industry and the Industrial Revolutions were really kicked off. We then moved on to mass production, which started around the 1870s, and it peaked around the 1909, 1910, in the automotive industry with Henry Ford. We saw mass production, we saw assembly line, high uses of electrical energy, and some early forms of mechatronics, which is mechanical devices, electromechanical devices in both in the plants, in assembly, as well as in the vehicle. By the early 1970s, around 1969, automation crept into the industry, and we saw robots, we saw robotics, we saw computers and electronics making greater usage in the industry, both in the actual final product as well as in the assembly and manufacturing. Fast forward to today, we see what is known as Industry 4, and it's all over. Everybody talks about Industry 4, and now there is even Industry 5. What we're looking at now in today's world is cyber physical systems. We're looking at Internet of Things. We're looking at networks, artificial intelligence. So we've got complexity. As you go forward in time, we have more complex systems that are talking to each other, layered on top of each other. For example, there now was known as ADAS, or Advanced Driver Assisted Systems, and we see also the rise of autonomous vehicles. So what is a risk here? As the complexity of the systems get greater, what is happening is for every new innovation, consumers are becoming more dependent on technology. For example, in the automotive world, if you look at something like a blind spot assist, as drivers move out of the lane, the blind spot indicates that they're out of the lane and the driver moves back into the lane. What happens is that over time, the driver or the consumer becomes very dependent on technology. If that fails and there's no redundant system mitigating it, then of course it could be catastrophic and end in a fatality. And for this reason, we see recalls happening daily, because what's happening is the complexity of the systems, they have failure modes that really need to be more detailed than ever before. Here's a quick glance in 2019, a window of time for the early part of 2019. And as you can see, I took examples of a spectrum across all the manufacturers. And what it was, it's use of all these complex systems where you had, for example, the auto brake, the electronic auto brake, non-engaging, unintended braking, brake boosters. These are all safety items. So this again shows you that the recalls that were happening was because of a lot of the increased use of the advanced driver assistance systems, or the ADAS. So what we see happening is an accelerated evolution. It's not so much that the risk is greater, but it's the rate of change, as the word acceleration implies. So things are happening at a faster rate, things are changing at a faster rate, and our current 4th edition that we have in North America has now become unable to meet the challenges of this new complex analysis that is required for risk mitigation. We're talking about 12 years ago, the golden standard was published, and it's still the playbook in use today. The other thing that is happening is the world is a global village. Supply chains are using different methodologies. Across in Europe, they're using the VDA. Over in North America, they are using the AIAG 4th edition. So there's a need for harmonization, because it's causing suppliers' costs go up, suppliers' complexities go up. They have to be on 2 different platforms, 2 different ways of looking at the same FMEA, even though they might be manufacturing the same component for both places. For example, the airbag manufacturers, they manufacture both for North America and they manufacture both for Europe. So they would have to be giving their FMEAs in 2 different methodologies, not just 2 different forms. And that's what I need to stress here. So there has to be some sort of harmonization for this to become effective. We look at warranty and recall costs. So we had over 11.8 billion in claims and over 10.3 billion in warranty accruals for 2016. Those are significant amounts. And if you look at it year over year, it was over a 26% increase over 2015. So we're looking at about a $22.1 billion. Now, most of these recalls are not high severity items, so they may not have been causing fatality, but still, if you look at the amount of cost that this is incurring, you'll realize that this is why we need to do better at risk mitigation. We look at the cost. The automotive OEMs, they're shouldering this cost, and recall notices have increased by as much as 4 times in the last 10 years if we look from 2007 to 2017. So again, this shows that there is a need for really drilling down and doing proper FMEAs, whether it's a PFMEA or a Dfmea. So we're doing our best, but we see recalls still happening. This slide here is taken with a courtesy from the web, and as you can see here, in 2017, airbags, we had about 97 recalls, and you know, look on the bottom of the screen, it's over 32 million vehicles, 33 million vehicles were affected, and most of the recalls for software and electronics, we're talking about 89 recalls of 2.5 million vehicles. So it is significant, and this is the reason why we need to take a step back and look at doing really a lot of analysis way up front in the design as well as process design, so that we can mitigate these failures from happening. As a quality practitioner, my My thing is always the cost of quality management system. We deal with cost of quality. So in this little diagram I have here, as you can see, there's a total cost of quality is divided in what I call cost of poor quality and cost of good quality. So cost of poor quality, the cost associated with poor quality is the internal failure costs and your external failure costs. What are internal failure costs? Internal failure costs, we're talking about the scrap, the rework as you produce, the refinishing, the rework, all those things, poor OEE, low first time yield, those are all internal costs, and you have to bear that as a manufacturer or a supplier. Then you have the external failure costs. So even though you've done your best, you've got the best processes, the quality management system in place, and everything, they're all lined up. You get complaints, as we saw in the previous slide, and you also saw warranty recalls. Now, the cost of good quality, on the other hand, is divided into two areas. One, your appraisal costs. This is all your inspection. You inspect, first piece, receiving inspection, in-process inspection, final inspection, doc audit, all those costs, all the inspection costs, layout costs, those are all the appraisal costs. And then you've got your prevention costs, which would be your implementation of your quality management system, managing the quality management system, training, all the other things, and doing specific analysis such as FMEA. So FMEA is one of the major prevention costs. One of the things I always look at, even though this has been preached over and over again, in any quality department, you will see that we always have a low amount of money that is invested in prevention costs, but yet we react when we get the external failure costs and we do the ADs and we try to close the loop, but it's oftentimes too late. So FMEAs is a powerful prevention costs mechanism that, ironically, once you have those prevention costs in place, then the external and internal failure costs would go down. So you do need to spend the time translated to money, hence the word cost. That's the way you'll be able to mitigate that failure. So FMEAs have a direct impact on the failure. So what do we need? So what do we need going forward? We have looked at what this FMEA is, why we need it. What we need is an integration of quality risk management. We need a systems approach at the organizational level, which combines the people, the processes, and the technology that are continuously flowing so that we can make it happen. The collaboration of people, the processes that you have, the established processes through a quality management system, through standards of operation, and the technology, the kind of technology that you're using, the kind of technology you're using right down to how are you doing the FMEAs, what do you have? Are you using a software? Are you using a chalkboard? Are you using spreadsheets? That is one of the technologies. How do you achieve that so that it can enhance the entire cycle of collaboration of people, process, and technology? So we need to make sure that people and processes, as you said, we look at a collaborative landscape. We need to have effective teamwork and collaboration. We need to be able to connect the customer, the design, and manufacturing all together so that we can all work as little cogs in that wheel. We need to make sure that when we have the FMEA, the action items are closed out. We need to use this as a knowledge management platform so that we can capture, we can share lessons learned, we can recycle it back from the field failures. We need to avoid all those repeat issues and recalls that we're getting. We need to be able to manage data properly. We need to get real-time data. We need to have data that is relevant, data that is on time, data that can be used to drive action. And we need to really take a look at how are we doing the FMEAs. What kind of tools are we using? Are we spending more time in the administrative effort of doing an FMEA? So I want to look at methodologies now. This is what the North America AIAG 4th edition of 2008, the last revision, the golden standard. And this is taken directly, hence I have the red star there, It's taken directly from the manual. It's called a process flow for FMEA, and they have 10 steps. It says you define the scope. What is a scope? You're defining the scope means what is in scope, what is out scope. What is it we're looking at? How far? So if you're doing a process FMEA, you're looking at the specific processes, the cells that are going to produce this from start to finish. You define the customer. When you define the customer, you define both the internal customer and the external customer. Internal customers are those that have your SLAs within your system, within your company, so that you will be able to mitigate any failures happening from station to station. You identify functions, requirements, and specification. So what are the functions? What are the requirements? What are the specification? What is this component going to be doing? What is a function of this process? How does this process convert from an input to an output and add value to this station? Identify, like I said, I was doing PFMEA here, right? We identify the potential failure modes of each process. We identify the causes. What is causing those failure modes? We look at the potential effect. What is going to happen if those failures are not mitigated? Then we look at our controls that we have in place. We identify and prioritize risk based on some methodology of severity, occurrence, and detection. And we recommend actions, and then of course we close it out and verify the results. So this is a 10-step approach of the AIAG 4th edition. And now we looked at this form, which is the AIAG form. Just want to have a quick look. As you can see, it starts off from left to right. It's a process step, function, requirement, mode, effect, cause of failure, controls for prevention, detection, your recommended action, and you've got your RPN or risk priority number. A risk priority number is the multiplicative result of the severity, occurrence, and detection, and those you can take from, as I said, the FMEA is an analytic method. So you've got a table, and from the tables you take the ranking, and that's how you rank it out of 10, 9, 8, from 1 to 10. Occurrence the same, and detection is the same. You multiply it out, and based on the numbers that you get, you can prioritize your actions based on the numbers. There is one thing here that that has led to some of the ineffectiveness of using this method like this with a form. What happens is invariably people just fill the form, they look at the headings, they say, okay, what's the failure mode? Oh, what's the failure effect? And then they go from left to right across the form, and they use the final number as the number to evaluate the risk without looking in depth at the severities. For example, if you have two different events, the first, the S is a 3, the O is a 2, and the D is a 3. We multiply those, we get 3 by 2 by 3, which is 18. The second one, the severity is a 6, the occurrence is a 1, the detection is a 3. We multiply 6 by 1 by 3, we get 18. However, you should note that the severity in the second case is 6. So are the risk implications of these two events different? And this is the issue. If you go by RPN alone, you will ignore that the second event may have more severity, which means the impact would be greater, whether it's to the plant that you ship at, whether it's your internal process. So this is why you need looking at RPNs can be very deceiving. The VDA 4.0 in FMEA in Europe, they use what is known as a 5 steps approach. And they looked at it from a system standpoint. They said, okay, the first thing we need to do is to have a structure analysis. What is the structure? Then for each aspect of the structure, what are the respective functions of each aspect of that structure? And then from those functions will fail. We will do a failure analysis. And they also had a severity, occurrence, and detection. And then they look at what is known as action analysis. So when action analysis is similar to the AIAG, you looked at what it is you have for prevention, detection, you look at your RPN number, and the last stage was optimization, where they looked at what is the current RPM and severity, occurrence, and detection, and what do you need to mitigate. So if you look at the form on the bottom, theirs was kind of different. They would just type below on the form in brackets the new occurrence, because in action items, whatever you do, you want to reduce that occurrence from happening. Invariably, you would not be able to in a process unless you change and put a brand new process, but you would not be able to change the severity of the impact of what's going to happen. If you don't make a part that is smooth, or does not make the hole is not drilled to the dimension, the impact is the same. But what you can do is change that occurrence, and your detection methods would reduce the frequency at which it can happen. So compare the two methodologies. What are the differences and similarities of the AIAG 4th edition and the VDA 4.0? So we look at it. The similarities, as we can see, is they both use the RPN method. The ranking tables may be slightly different. The other similarity we see is the approach is, you look at the analysis, what is the prevention, what is the detection, and you also look at requirements. However, the difference is that in the VDA, they are looking at it more from a system standpoint. They look at a structure analysis, which means they look at all aspects of the assembly, and they look at functions. And the way they look at it is that functions, if something has a function and that function is an intended function that will lend to your customer satisfaction, if that function is not met, then you will have a failure. And that failure is the failure mode, and that is a failure mode you need to mitigate. In the AIAG VDA, 4th edition, you tend to look more as the requirements and specifications that were not met, not so much as the function. So if the requirements and specifications are not met, then there was a failure, and then you look at the impact of the failure from that. So those were some of the little nuances, but it is not really nuances. One is definitely a more powerful approach because you're looking at a systems approach. Now, when we look at the merged new AIAG and VDA guideline, as I will show you later on, what is it reflective of? It generally, I would say that about 80% of the content of the VDA was inherited by the new AIAG and VDA merged approach. So structure analysis, and you will see later on as I go on, you will see structure analysis, function analysis, failure analysis, and optimization. That was what were the drivers for the new AIAG and VDA. So changes. The current 4th edition, because as we saw, it's been around for the last 11 years, over 2 decades, 1 decade, sorry, over 1 decade, 11 years. Changes are evident, and so the new guideline is giving changes, and with change comes change management, with change comes rejection. And so right now there's a lot of flux in the industry. As I speak to you in May of 2020, there's a lot of flux in the industry, and the SAE J1739, they are looking to come out with their own standard. The AIAG and VDA guidelines are being reviewed again, because some of the OEMs and some of the supply chain are not able to adapt it as easily, and in many cases, no one wants to have change. So we are probably going to see CSRs, or customer specific requirements, that will be changing and evolving with the passage of time. So here is the AIAG and VDA approach that was published in the AIAG Rev 1 in 2019, and this is taken directly out of the manual. So the 7 steps are the preparation, project planning, structure analysis, function analysis, failure analysis, risk analysis, optimization, and result documentation. As you look at it, you can see the inheritance of steps 1, 2, 3, 4, and 5 came directly out of the VDA, more or less. And optimization has taken a slightly different approach. It's a mix of the current 4th edition and some of the VDA. And the last step that he added was result documentation, which is completely new for both the VDA and the AIG 4th edition. So here is a general high summary, and again, this is taken out of the manual. The 7 steps. So the 7 steps are system analysis, failure analysis and risk mitigation, and risk communication. And in those, for system analysis, you've got your planning and preparation, your structure analysis, your function analysis, if you were to group it. And under failure analysis and risk mitigation, you've got your failure analysis, risk analysis, and optimization. That makes 6. And the last one is risk communication. So I will go through each one of these. However, why did they add risk communication? As you know, this here is really communicating the entire FMEAs after it's finished in terms of the risk. So the management is quite aware and well aware of the risk for each FMEA that is finished. Some may say that this is overkill, because prior to this in the IATF 16949 and the earlier standards, the TS and even the QS, we would have management reviews and we would review on a high level some of the failures that we were getting from the FMEAs, some of the failures we're getting from assembly manufacturing failures as part of our management review. However, in this new methodology, what you're looking at is actually communicating the risk after each FMEA cycle has been completed. So the PFMEA in the new guideline is cascaded throughout the supply chain, and again, this is taken directly from the book, the book that was published last year. As you can see, the failure, you know, from customer to tier N+1, so it could be tier 5, tier 4, tier 6, etc., all the way through, it's cascaded. And the goal here is to have a collaboration between the customer and the supplier. So you may be way up in the supply chain at tier 4, but you have an impact on the end customer. So the severity is what we're looking at. The severity of the impact for each one of those items or each one of the legs in the relay chain all the way to the customer is what is important. And the goal going upwards through the chain is to reduce the risk to the end customer. And again, we look at PFMEAs in contrast to Dfmeas. The main thing to remember here is the Dfmea. If you're doing both the Dfmea and the PFMEA, the Dfmea needs to be linked to the PFMEA at all times, because you need to understand what is the design intent. And when we look at process FMEA, is how can I have process in place to ensure that the design intent is met. That is important. So for example, if the design is a 6 millimeter hole plus or minus 0.1 millimeter hole, then the process that you have has to be consistent, it has to be repeatable and reproducible, so that if you make one part or you make 10,000 parts, you will have that 6 millimeter plus or minus 0.1. So the design intent would have been met by the processes that you have employed. So that is where the process FMEA takes into consideration. When you're looking at the Dfmea, you look at the hole, you set the tolerance at that point, because you say, okay, if I make the hole 6 plus or minus 0.2 and I have a 6.2 hole, then it would be too loose at the maximum condition, the maximum material condition, it would be too loose, and hence it would not work and it would cause a problem. So you have just passed on that design down to the PFMEA. So in the preparation and project planning, step 1, this is the first step. What you need to do is look at what is known as the 5 T's. And again, this is taken directly out of the book, and on the left side, I've kind of aligned it with the FMEA timing of the APQP phases. So if you will see here clearly that when you're planning and define the program, it's very important to understand the information flow from the Dfmea to the PFMEA. And the product design and development verification throughout, you need to have, once the production concept is well understood, you need to start putting pen to paper, and you need to understand how the process is going to deliver that which was designed. So this is very important to align the FMEA with the APQP phases. So in the very first thing, we look at the first T, which is called intent. Why are we doing the FMEA? We need to understand why. Why are we doing this FMEA? What is the driver for this FMEA? When is the FMEA due? That's the timing. The team. Who do we need to be on the team? And you will need to have people on the team that are SMEs, people who can facilitate, people who can negotiate, people who have an understanding of the processes, as well as an understanding of the design. So the cross-functional, or what we call the MDT, or multidisciplinary team, needs to be there so that we can achieve a very effective risk management method, or risk management analysis. The task, what needs to be done, and then of course the tools, what are we going to use to conduct the analysis. So at this point in time you need to choose that. So in project, it is a project, so you choose in the project the 5 T's and you make sure that those things are clear, and then you start your FMEA. One of the things that makes it very easy to start it off and come out of the gate running is that you should have some sort of templates and hierarchy, and this is suggested in the new guideline as well. It was in the old AIG 4th edition, but there was not a lot of emphasis, but people by default made those in industry anyway. So you've got like a foundation, then you have a family, a system, a plant, regional, CSR, customer service requirements, and for each one of those you will have like different FMEAs. So FMEAs, the way this idea is, let's say for example you're a manufacturer of I don't know, pens, mechanical pens, and at a foundation level, when you look at the function of the and you look at the system structure and you look at the function, you look at it in a very generic fashion, and you said, okay, the function of the pen is to write, and each one of the systems that we have within there, the spring that has to press the mechanical pencil out, you'll have a function of each one of those aspects, of each one of those components within the system, each one of the methodology that you're using or processes rather, each one of the processes that you're using for the assembly. You will have different functions of each process, and they will have respective failures. So when you come out of the foundation, you have that high level foundation FMEAs. Now we could look at the family FMEAs. So let's say, for example, you're making mechanical pencils, but they're made, you're making plastic mechanical pencils, and you're making metal or mix metal and plastic. So now you will have a family, because the family FMEAs will take into consideration all the functions that were done at the foundation level, but now at the family level, you will now be doing specific to plastic, specific to metal, and then you start to get an understanding as you get down to a plant level, you get a regional level, geographical level, or customer specific requirement. So if you're supplying the pencil to manufacturer or assembler A versus assembler B, like you sending it to Ford versus GM versus Chrysler, each one of these would have specific requirements, and each one of those requirements would be embodied in terms of what you're using for significant characteristics or critical characteristics would be embodied. So the idea here is when you go to do the FMEA, you look at it and say, okay, this process FMEA, what is it am I doing? Am I doing a family? So you don't have to go and start back over again. You would have inherited everything that's on the foundation, the family, and the system. So it's very essential in the planning stages. One of the other things that makes this a very powerful tool is that from field failures and from complaints and warranty, when you do an 8D or you do preventive corrective action or do some sort of root cause analysis, you feed it back to the respective level of the FMEA families that you have. So it could be at a plant, it could be a family level, foundation level. What this does, increases the efficiency, which means the speed at which you can do your FMEAs, and also the effectiveness, which means the FMEA has mitigated most of the known risks, and you don't waste a lot of time doing and considering risks that are not relevant to the system, and it helps you with your scope. So we talk about a systems approach at the organization level, and now we're looking at system approach at the assembly level. So everything is a system. So for example, this diagram you see here is an exploded view of a brake assembly, and it has the axle, it has the disc, it has the pad, and of course the caliper. Each one of those are sub-assemblies, and each one of those have components, and each of those components have different functions. yet each one of those functions are interrelated with each other and they transfer. So when you look at your FMEA, what we're saying is you need to create your structure tree. You need to say, okay, how is this structure going to work? Here is my system, my subsystem. You may be a manufacturer, for example, of brake pad. If you're a manufacturer of the brake pad, what you're doing is saying, okay, what is the function of my brake pad? What is the higher level? What is the next level up? What is the next level down? And that is where I will start to see the severity, the failure effect is always to the higher level up. In this case, let's say the brake pad. The brake pad, the higher level up would be the caliper assembly. The lower level down would be the disc. So when we look at the failure mode, what it is, we look at this diagram, it says that if the pad fails, then the effect would be on the caliper, and then the caliper, the lower level of the caliper has to drive the axle, has to stop. It would fail to stop. And then of course we can go up to the higher level of the vehicle, which means the vehicle will not stop. And what is the severity? The severity could be a 9 or a 10, which means it could be loss of life. Now when we look at the cause, why did the brake assembly fail? And I'm looking not in design, I'm looking at specifically here, I'm looking at process. So there may be some sort of a baking technology on the pad, that the pad has to be baked on to the back of the plate, and in that process it was not done correctly, so the pad became loose, and as a result of that it failed. And this is what we call the M's. So when we look at failures in the new methodology, they say look at the 4 M's. The 4 M's are man, machine, material, and milieu, with a French word for environment. So those are the 4 M's that you look at. And those are the causes, or where the causes would be coming from. So you have your failure mode, what can go wrong, the effect of the severity, what's going to happen if this failure mode occurs, and where does it come from? Is it coming from the way it was done? Is it man, machine, material, or milieu, the environment in which it was done? So we're talking about function and requirements. One of the things people get mixed up with is a function and a requirement. Now, a function of a process is basically in the present tense. It's kind of, I'm going to be doing this to this. So for example, I'm going to be, the function of this process is to drill a hole, or is to apply glue, or is to insert a dowel, or is to polish the surface. Those are all functions. Requirements, on the other hand, we're now talking about, anything that is maybe some sort of regulatory standard, customer specific need, a customer specification. It could be internal, it could be from your design and manufacturing. So those are the actual functions. For example, you might say, okay, the hole has to be bore free. So this function is to drill the hole, but the requirements of that hole is for it to be bore free, or is to be 6 millimeters plus or minus 1. So you've got a function. So when you get a failure, you don't get the failure on the requirements, you get the failure of the function, that the press did not drill the hole to the requirements. So you have the failure, and then you would have all the 4 M's that go along with that function. So what failed? Did the machine fail? Did the drill fail? Did the human fail? Did they fail to remove the burr manually through the deburring operation? So this is how the failure mode effect analysis on the PFMEA is done. So there's 2 diagrams here, and not to be confused, taking it again directly out of the book. When you're preparing and you're planning at this very first stage, you want to look at all your different process level. You want to look at what it is I'm assembling. You want to look at, is it in a U? You want to do your flow layout. Is it in a U-shaped cell? And then you can look at the parameter diagram. As you can see there, there's the input on the left and the output on the right. The input and the output, the desired output, and what is the process in this example, which is taken directly out of the book. It's for a sintered bearing, and the press is pushing the bearing in, and at the end they want to make sure that it's all assembled the way it should. And the process noise factors, as they call them, the 4M, the things that would influence the correct uh, uh, process of making this press fit is the operator, it could be the machine, it could be the material, and it could be the environment. And in this case, where they say, well, okay, if I have a failure, it means that the operator was not trained, the operator did not do it properly, did not follow your instructions. If the machine failed, then it could be from poor maintenance because it was wear. Maybe the drill was not, the press was not done to the right pressure. It was not doing it correctly. The material, I could be using material that has variation, material that is not correct, material that has inclusions, so I'm not getting it. And then the environment, so maybe the temperature at which it was done was incorrect. So now it's not working the way it should. So that is where the preparation and planning, and you can put this in a P diagram, and at the bottom you put the requirements, and that's how that. Steps 2, 3, and 4. So in steps 2, 3, and 4, we're looking at a structure analysis. The structure analysis is breaking down the system. So we're looking at the system, and we're looking also at, in the process, what is required. So for example, if you're using, in this example here, the system is the motor assembly, and then there's the bearing to be pressed in, and the work element type is an operator. So we're looking at a structure analysis. We're looking at each process, what needs to be done, what is the name of the subsystem, and what aspect of those 4 M's are being involved. Then we look at the function. So for each one of the process items that were identified, we have a function. So the function is always 3 basic things. You look at your plant internally, then you look at the ship to plant, if you're going to ship to, let's say, Honda or Ford, and then we look at the end user, the person who's actually going to use this. So for example, this thing that you're making is going all the way into a window lifter. So you have to put your task is to put a bearing up onto a pole, and so at your plant, that's the function of the system. The next thing is at the ship to plant, they have to assemble that shaft and bearing onto the window lift assembly, and at the end user needs to make sure that all they want, the intended function of the entire window assembly, is for it to roll up and down when they press a button. So we have those functions, and then when we look at those functions, the next step is look at the failure analysis. And in the failure analysis, we say, okay, so what happened? Well, the clearance was too small, so when they assemble it, it did not assemble the way it should. And as you can see, the same thing happened at the assembly plant. We could have failures at the assembly plant, and of course at the end user, suddenly they tried to pull the window up with the button, and it got jammed. So as we look at it, we look at all of the failure modes that are going to contribute to the in-plant, the ship-to-plant, and the end user. And from this, we can then look at what was the failure cause. So if we link the failure cause directly to the 4 M's, we will see that maybe the assembly was incorrect because the machine did not do what it was supposed to do. And that is how we start to look at the relationship between the failure mode and the failure cause and the failure effect. There you have on the guideline in the manual, they show you those little, for example, there's a bulb. The bulb has 3 parts. There's LED bulb. It has the top half, the middle part, and the screw at the bottom. And that's the structure. Each one of those 3 pieces in that subsystem would have its function. And we identify the functions at each level. When it's all assembled, it's supposed to light. And of course, in the failure analysis, they show it in red, meaning that, as a reminder, it did not work. Steps 5, 6, and 7. After we've done the analysis and we looked at the failure modes and the failure cause and the failure effect, we then put numbers so that we can create some kind of ranking. And if you remember, the Fmea is actually a discipline method that applies some sort of a ranking method to indicate to you what actions need to be prioritized. So in this case, we look at the failure analysis. We attach based on the tables what the severity is, what the occurrence is, what the detection is. The occurrence would be based, of course, on what kind of mechanism you have in your prevention and detection, as well as past history, past complaints, trends, and then the action priority would give you that prioritization of the action that needs to be done. Then we look at optimization. In optimization, we are looking at mitigation of the risk. How can we, after we have identified certain actions that need to be done, how can we mitigate these risks? And when we mitigate these risks, we need to close out the actions, and we also need to have pointer to evidence, and we need to put some sort of remarks. It's very important that you have the pointer to evidence, because it tells you that this is what was done, and there is evidence of it. You just can't say, well, yes, I did it, and it moved from a 5 to a 4. The occurrence now moved from a 5 to a 4. You need to show that you did some sort of testing, you did some kind of process capability study, you did something to show that you had made that improvement and mitigated that risk. And then the final stage, of course, is the result documentation. And in the result documentation, because it's a project, you come back full square, full loop, and you look back at your 5 T's and you comment on each of that. That is the basis of your report. The intent, the timing, the team, the task, the tool. So were these things met? Were the objectives of the project met? And you need to prepare a report to management, and you need to reflect back on the scope and results of the project plan. You need to talk about how the functions in the fields were developed, and you need to plan to address and close out any items that may be still left on the action priority list. One of the other things that you want to do is collate all the high risk levels. You really want to make the report impactful so that everyone knows, especially at the upper management level, those areas of risk that you have addressed. The additional considerations that you have to make, as known as visual trees, they said, try to make everything visual. So when you break up your structure tree, you can put your focus elements, you can look at the way the structure is, and then you can show your function nets and your failure nets. And this sort of structure analysis helps you greatly when you're looking at root cause analysis and understanding your system. And it also allows you to build linkages directly from the Dfmea to the PFMEA. Here are your severity tables. As you can see, it's from 10 to 1. So in the process, the failure at 10, may result in plant regulatory non-compliance. So, you've got some regulatory compliance in plant for health and safety of the workers up in Canada. There are very strict regulations in the Act and the regulations, and you need to meet those. And if you're not going to meet it, then the impact goes to your plant. It's a 9. It's a 10 or a 9. Also, if it meets to the failure at the ship to plant, and again, end user. So here you see the severity is broken up into impact to the plant, impact to the ship to, and impact to the end user. And so for each one of these ranking, you put the severity from 10 to 1. In the case of the occurrence, it starts from extremely high to extremely low on a 1 to 10 scale. If you've got absolutely no prevention controls, then it's a 10. It means it's a high occurrence. The probability of occurrence is very high. And if you have controls that are very effective in preventing failure, and you've tested that, and you're showing that it will never happen, then that becomes extremely low. These are not subjective, by the way. These are actually from past history, from past complaints, your system, how robust your system is, and that's how you rank it. Again, we've got the detection tables. If you've got very low detection, then it's a 10. And if you've got very high detection, it's a high. So very high detection could be automatic gauging. It could be a poke-yoke. Whereas very low, you don't have a proper, it's for the process design, you're depending on things like human tactile or something going off or a light coming on. and manual gauging. So this is very, very important when you do the acid test of your system, your detection. You want to make sure your detections are in the range of 432, and if you really look at the tables, you will see that in fact it's talking about prevention methods, system design, or process design rather. Process design should be able to really have systems in place to not and to mitigate any potential failures. Action priority tables. As you can see, this is a permutation of the severity, occurrence, and detection, and the table is different from the old AIAG 4th edition. It's no longer multiplying S times O times D. For example, if you have a moderate, and I choose that one, a 9 and 10 severity with occurrence of 4 to 5, and then it's the ability to detect this is very high, then it becomes an M. So you can have an H, an M, and an L, and that's your action priority tables. So one of the things to note, and I've taken directly out of the AIG guideline, it is not a prioritization of the risk. So it is not a prioritization of the risks. It's not a risk of 10 or a risk of 9 or a risk of 8, a risk of medium or a risk of low. What it is the actions to reduce the risk. And that's very important to remember. So I have, if the action is a high action, I need to take action right away, or it's a low action, I don't need to take action. So what are the limitations and weaknesses of FMEAs or PFMEAs in general? We always talk about the Dfmea side of things and the PFMEA side of things. I had the experience of working on both teams, and I've been working with more or less 80% of the time I've spent in process. I've spent a lot of time on the APQP teams, and it's very important in the very early stages that you get your voice heard, that you are in fact in the design, you're using effective DFMs or design for manufacturing, so that when you get to the manufacturing, you can produce those parts. So it's not done in a vacuum. So you can't correct a weak product design by focusing on a super robust process. In other words, you say, as a design engineer, oh, well, you know what, those guys are going to get rid of it when it gets to the manufacturing side of things. No, it will not be able to be eliminated or reduced or mitigated because your processes do not match what you are in fact designing, or you have not taken into consideration design for manufacturing. On the flip side, you cannot, having said that, I mean, if you've got a design but you've got weak processes, you can't expect that you can correct the weak process design by focusing on design changes to the product. You can't say, well, you know what, I can't meet a tolerance of 6 plus or minus 0.1, so you better change your design to 6 plus or minus 0.5. Now that's not going to work. You need to make sure that your process is able to deliver it, or borrowing or deborrowing or errors. Or so the important thing to notice here is that both teams have to work together. They have to work effectively on that APQP team. So you need some sort of collaborative platform. You need to spend a dedicated time so that you are able to provide the design intent of that assembly, the design intent in terms of its function to the end user. So, it is only as good as a team that is behind it. The multidisciplinary team has to be one that has gone through the stages of forming, norming, storming, and performing. They need to go through that stage. The team needs to be a well-matured team, and they need to be able to have a good working relationship so that they can effectively get rid and mitigate of some of those issues. Any issue that is beyond the team members' knowledge, you don't know what you do not know, and you will not be able to consider things that are out of your spectrum of knowledge. One of the things you need to do is to make sure that you have access to other resources within the organization or outside the organization that can help you. And again, if you forget to list any of your failure mode, of course, it will be totally ignored, and it will have to come up when you get a complaint or a recall. So One thing to remember is that the FMEA, whether you're using AIAG 4th edition or you're using the AIAG VDA Guideline, it is just a method of prioritizing the failures according to the risk. It does not eliminate the failure modes. The failure modes will still be there. The failure modes will still be there. However, you can reduce their recurrence. And again, the team may require things that are way beyond their skill sets that they will need to have help from outside. So, in summary, we look at the changes from the AIAG 4th edition to the AIAG VDA Guideline. Here are the changes and some of the rationale that was used. So the form header was changed, and that is so that they can have standardized information for record management. Structure analysis has been linked to all levels because we're now looking at a system approach, and the subsystem, it's a more detailed analysis. We are now looking at function analysis because you want to make sure that if you understand your system, you understand your function. Failure analysis, it talks about the failure effects, failure modes, and failure cause. They're all linked within the structure. Risk analysis, like in the example I showed you for 18, 6 by 1 by 3 versus 3 by 2 by 3. RPN is no longer just the benchmark. The API gives you a little more room to understand and treat severity and occurrence, because severity is now the driver and occurrence as well. Optimization, the recommended action is split into prevention and detection and continual improvement. So you can manage your action evidence-based considering the entire structure and linkages. Result documentation, very important step because it's direct communication to upper management. And in the 7-step approach, they have the result documentation added, so it's easy to link to your APQP. One of the things that changes, they remove the special characteristics from the Dfmea, however it remains in the PFMEA. And the special characteristics, because it's more of a requirement, the FMEA is talking about dealing with functions, and functions have failures rather than specifications having failures. This is one of the reasons it was removed. However, you still have it on the drawing, so when you get to the PFMEA, you will have to make sure that you meet those special characteristics. It's extended to the tiered suppliers, and you need to have full collaboration from suppliers to the end customer. And that is basically to the depth I want to go into to give you that overview of FMEAs and PFMEA in specifically. The Dfmea is slightly different. However, the methodology of higher function and lower function and failed focus element is still there. And so with that, I thank you very much for listening to this. Please send your comments. And once again, thank you very much.